GPS observation C.
Okay, hi everybody. Thank you to the session organizers and to the conference organizers for putting this on. I'm very excited to talk with you all today about some sensitivity kernels and my ongoing work looking at the adjoint-based method to figure out just what exactly the GPS observations are going to be sensing. And I want to highlight and give a shout out to Andrew Lloyd, who's over there. Do you want to wave, Andrew? And a number of times I'm going to mention to please come see Andrew's poster, number 238, later this afternoon. So thank you to Andrew. Okay. Let's see. I should say I feel very lucky to have gone after Grace and Micah because you already know all of this, so this is great. But as a member of the GIA community, we study this response of the solid Earth, this viscoelastic deformation of the mantle, to changing surface loads. So as H2O mass is exchanged between ice sheet reservoirs and ocean reservoirs, that leads to deformation of the solid Earth rotation axis and gravitational potential field. And so this is very important for a number of things, but we have these broad picture goals as a community and as members of humanity, I suppose. We want to constrain the past ice loading. We want to estimate modern ice mass fluxes. And really, we want to be able to accurately project future sea level changes. And for all of this, we need to better understand, have a better handle on those two inputs into our GIA modeling efforts. So those are the rheological constraints of the viscoelastic mantle structure and the ice loading history itself. No, yes. Okay. So I think all of us are interested in Antarctica. It's a fantastic place to study. It's my favorite continent. And it's interesting for a number of reasons, but one is that it has this very interesting structure in the mantle underneath this ice sheet that's blanketing the continent. There's, the East Antarctic is this cratonic-like region, compared with the West, which is very different, and it's this failed rift system that's underlain by this inferred thermal upwelling, maybe hotspot, maybe not. But this tectonic setting means that there's very interesting solid Earth structure, which is going to really impact, for example, as we just heard, the ice sheet evolution, the sea level predictions, and of particular interest to me, the GPS uplift rate. So this solid surface deformation that results due to the rebound in our bouncing balls here. That's great. Okay. So we do have this fantastic data set in this, otherwise pretty limited region of constraints, right? It's very hard to get a sea level record if there's an ice sheet on top of your raised beach. But we do have this PolNet data set, which is measuring crustal deformation at stations like this one with the little penguin. And you can see there's pretty good coverage of the Antarctic Peninsula, the Transantarctic Mountains, and along the coast, especially in the West Antarctic here, which is where I'm going to be looking at mostly. And the important thing here is that this data set can be leveraged to constrain these GIA inputs, which are really important for these bigger picture questions. And I could, and I have, given an entire talk about the viscosity structure, but today we're just going to focus on the ice load itself. Please see Andrew Lloyd's poster, number 238, later today if you want to learn more about the viscosity. Okay, as Grace already talked about, and Micah did too, we think about the mantle in terms of sort of two paradigms that I'm going to talk about. This sort of onion skin view of the world, where Earth structure, mantle viscosity varies only with depth. If we want to think about a more realistic Earth structure, we know that Earth has lateral and depth varying viscosity. The issue, though, is that we are able to, we're able to use sea level solvers that can be quite fast, these love number calculators. Whereas the moment you want to go towards these more realistic 3D structures, we have to go to computationally expensive solvers. So take your finite element, finite volume, spectral element, take your pick, but it's going to take supercomputing time and it's going to take a while. For the sake of consistency and timing in this talk, I'm only going to talk about results from this spectral element code, even for models where we consider 1D structure. Okay, so I'm going to bring up my motivating question again and break it down a little bit more, which is how far away from the station, a given station, and how far back in time do you have to go before ice load changes will negligibly or only partially, slightly, impact the observed present-day uplift rates? How far back in time do you have to go? How far away do you have to go? So when and where? In terms of where, we can hypothesize pretty proximal to this station. That makes sense. But if so, on what length scale? Like a glacier catchment, a drainage basin, the entire ice sheet? Put in context for me, the state of New Jersey, where I'm living now, state of Texas, where I'm from, the entire Western USA, where I guess I want to end up. Who knows? In terms of when, we can hypothesize based on what we know about, for example, characteristic timescales of the mantle viscosity, thousands of years, sort of this, late Holocene ice signal. But we know it's going to be dependent upon the mantle viscosity that we impose. And that really leads to my big question, which what effect will 3D variations in viscosity have? Is it going to be sort of one number, or is it going to vary with space? So I will answer this question. Okay, so how can we rigorously determine where GPS observations see the ice load? The answer is with math. So I'm going to go through this pretty quickly, but we have this representation of GPS observation sensitivity to ice sheet changes, where we have this perturbation in an observable, in this case, uplift rates at a GPS station. We can map perturbations to the rate of change of ice thickness to our observation via what's called the sensitivity kernel. So big takeaway is that if this kernel is larger, that means that a given change in the ice sheet condition will lead to a bigger change in the observable in the present day. Okay, and great. We want to be able to calculate this kernel, this property. The issue, though, is that it's very difficult to calculate, or it has been in the past. The standard approach would be to take a finite difference method where you run many, many, many forward models and perturb each grid element at a time and find out how your end result changes. And for the calculations I'm going to show today, it would take over 1.2 million forward models, even at pretty low spatial resolution, so it's really not feasible. Alternatively, we can turn to adjoint-based methods, which allow for direct calculation of these sensitivity kernels. The equations were recently derived, and they only require the forward computation the computation expense of 2 forward models, the forward and adjoint calculation. I'll just throw up the math really quick to say, look, we can calculate it directly. Fantastic. Let's move on. Okay, so as our example, let's consider these 3 GPS stations, so one in the Amundsen Sea, one in the Ross Sea, one in the Weddell Sea, and ask what are their spatial and temporal sensitivities to ice loading changes. So as our inputs, we have the spatial temporal history of ice cover, model of mantle viscosity structure. We're going to test 3 different values, and here are some results. So this is the length scale, I suppose, over which this station see loading changes, which is about the size of Texas, I'll note. So that's great. And how does it vary through time? Going through one at a time, so this is our stiffer model, our intermediate, and our weakest model. And we can see that the sensitivity is highest near the present day, and it asymptotically approaches a non-zero value as you go further back in time. But this is for the uplift, not really the uplift rate. If we want to know about uplift rate, we'd take the gradient, the derivative of this field, plotting here that derivative at 250 years ago. So this is how ice sheet value would change, your GPS observation would change given ice load changing at 250 years ago. And you can see sensitivity increases as you decrease the viscosity structure, which is what we would expect. Okay, and again, this is about the length scale, so I'm glad we answered that question. Okay, what we want to know, though, is this time threshold. So how far back in time do we have to care about the ice load? And to do that, we've imposed a constraint where we find 10% of the maximum sensitivity value, always found at the present day, and we're able to diagnose then this threshold after which we no longer really need to care about ice floating changes. So you can see that these values depend upon the mantle structure, as we expected, going from about 7,000 years to 750 years. Oh, I'm running out of time. Okay, I'm going to skip through the ice history question and get to the more interesting one and say, how does it depend upon 3D structure? So here is our input 3D Earth viscosity model. See under Lloyd's poster for more details, please, number 238. Okay, and here are the results. So once again, we see length scales, similar to what we saw before, about the size of Texas. And we see that the sensitivity is greater in models where the viscosity is weaker, as we saw before. However, jumping to this guy, we see this threshold for the 3D model is between, well, it's about 3,700 years. But this is for the value directly underneath the station. And we would not expect necessarily for that to be just one number in the 3D model case. So does this vary through time? Yes, it does. Okay, great. So what we see for the 1D model is we have about 8,000 years. We have to go back in time to be able to predict how this GPS observation is going to be changing. For the 3D model, proximal to it, you only actually have to care about, say, the last 4,000 years. And that value decreases as you go towards regions of higher viscosity. I'm out of time, so I'll just leave this here. But I want to say our goal is to create a sort of gallery of these kinds of, I call them back-in-time maps, so that if you're, say, looking at ice changes, and like Kier's talk yesterday, looking at this retreat or the thinning of the ice sheets, can you say, do GPS observations see it, yes or no? So that's the goal here. All right, thank you.
Thank you. I think in the interest of time, we'll keep moving along with our next speaker, or